Thank you, Rasmus, for the kind words of introduction. And yeah, good afternoon, everyone. As Rasmus said, I'm Matthias. I used to be an MSCi employee for 3 years. But as far as my experience with GC goes, I finished my PhD at the University of Umeå, and there I got to be in contact with this high resolution LICO mass spectrometer, which at that time was not ready for GC. But then later on there, I started a postdoc, and I used the same instrument with the thermal modulator, so to do comprehensive two-dimensional gas chromatography. And then after that, I went to Copenhagen as a change of scenario. No offense to Sweden or at any level. And there at MSCi, I used to also cover parts of my profile dealing with the two-dimensional gas chromatography, but more on the sort of the surface, not too much. Maybe running some demos, sometimes relying on my experience with GC. And then I decided to change scenario. So I moved here to Pisa, and then here I'm using the Agilent QTOF. If there are any LICO people listening to this, I'm really sorry. That's also no offense, and please don't take it as a as a betrayal or any kind of stuff like that. It wasn't really meant that way. It's just sort of life turned out for me this way. So that's just a little introduction to kind of alleviate possible political issues here. So let me just jump to my presentation quickly. So I feel very happy and privileged to talk about this very exciting and very powerful topic of GC. And I would like to thank you, of course, Rasmus, Thor, and everybody at MSCi to give me this opportunity to talk about this technique. So it's kind of difficult to try to condense and distill everything down to 40 minutes about two-dimensional comprehensive gas chromatography. Well, I'll try my best. First, I'm going to put things into a historical perspective, give some overview, talk about basically the instrumentation and some conceptual basics of the technique, and later talk a little bit about the types of modulation that are possible to use. And then maybe later, if need be, we can talk about some possible applications that are used throughout all topics of science and separation techniques. So what is multidimensional GC? I mean, this is a more collective term. Comprehensive GC is a part of subset of this concept called the multidimensional gas chromatography. So here on this slide, we can see a general setup of the gas chromatographic instrument. And we all know that it starts with some kind of injection. It could be a liquid injection or thermal desorption, etc. There are all sorts of injection types that are performed in gas chromatography. Then you have your column where the separation takes place. This column is usually placed in a temperature-controlled environment. And then you have some kind of detector. It could be a universal detector like flame ionization detector, electron capture detector, element-specific detectors, or a mass spectrometer, which we will also focus on this session quite a bit. So what if we want to add more selectivity and more separation power to our gas chromatography method, because we need it, because our sample is way too complicated and we have super busy matrix where it's very difficult to get some valuable information out. And we can do that by introducing another dimension of separation. And then this we would do by installing a secondary column with different kind of selectivity, so a different kind of stationary phase. So another aspect that is very important when it comes to multidimensional gas chromatography is to add some kind of transfer device. And this does not only connect the two columns, but it also refocuses the sample that is eluting from the first column. This is very important because this gives a lot higher separation power, plus potentially boosting also the sensitivity and the detectability of our methods. So in comprehensive GC by GC, this is called the modulator, but in hard cutting GC, or otherwise known as GC-GC, it can be a Dean switch or a cryo trap. So again, what is two-dimensional GC? Dual column setup with differently selective columns with some form of transfer device in between to facilitate the connection and the refocusing of the chemicals. So why would we opt for using such an instrumentation? And obviously, as I mentioned earlier, it's very useful for the analysis of complex samples when you have too many coelutions, heavy matrix effect. So if you have a headspace sample with 7 chemicals and basically 0 background, you can just use a regular old GC. Don't fire at a tiny sparrow with an artillery cannon. So when we are doing qualitative and unknowns analysis of complicated samples, it's very useful by adding increased separation power, either by adding dimensions of separation with hard cutting GC, or by multiplying peak capacities, like I will demonstrate later with comprehensive two-dimensional GC. This will make identification and peak mining much easier using this technique. And as an extra feature, we can also get out some interesting chemical information based on the chromatographic data while correlating certain physicochemical properties with retention time values. So just a quick reminder of what are the usual types of stationary phases that are available for capillary chromatography. Most of the applications are done either on a DB5 or a DB1 type column. They have different names depending on the manufacturer. These are called apolar type columns. Then you have aromatic type columns where you have some substituents instead of dimethyl siloxane groups here at different percentages. Or you have the polar type columns. You would have polyethylene glycol based or cyano based stationary phases. So this is kind of important to know. And if we are doing multidimensional gas chromatography, a combination of either of these, a combination of 2 of either of these stationary phase types can be very powerful in separating chemicals. Just a quick mention to about the EasyGC on the Rastec website. Maybe some of you know this software. If you're beginning to develop a method for the analysis, whether it's single or multidimensional GC, this is a very important and useful tool to start with. You just name your chemicals that you would want to separate, and then the software will spit you back recommended parameters for the separation of these chemicals. So honorable mention to hard cuttings or GC-GC. This is sort of a proto-comprehensive GC-GC technique. This is basically a technique where, let's say you have a very, very busy part of your chromatogram where you cannot possibly separate two chemicals or more using one column. Then you basically trap sections of these chromatogram either with the Dean switch or with a cryo trap, and then re-inject them into a column with a different selectivity stationary phase. Now, a good example for this is the full congener analysis of polychlorinated biphenyls. My inner environmental chemist wants to pop out, so I want to, give space to this. These are highly bioaccumulative and persistent organic pollutants that act as endocrine disruptors that were manufactured throughout the 20th century. And there are some standardized methods for the separation of these chemicals, and one of them being a hard cutting method. And it's performed by separating certain fractions of this first dimensional chromatograms. And once this run is over, then these chemicals are re-injected into a column with a different stationary phase, and then full congener analysis is possible. So now this is very nice, but the problem with this method is that these PCBs have already partially been separated from each other, even though we couldn't get baseline separation. So the challenge was how to basically keep the first dimension separation in a multidimensional gas chromatographic method. So as a response to this, pioneers of multidimensional gas chromatography started working on this device that became known as the modulator, spearheaded by Zoex in collaboration with LICO. And they made the modulator. This device will facilitate the refocusing and the connection between the two columns in a way that the first dimension separation is not lost. There are two main types of this modulator. One is called the thermal or cryogenic modulator, which facilitates modulation by the manipulation of temperature. And the other major type of modulator is called the flow modulator. Not so surprisingly, facilitates modulation by manipulating the carrier gas flow. I will talk about this a bit later. So what is happening here? What does the modulator do? So imagine this as your first dimension peak on your regular GC chromatogram. What the modulator does, it slices up this chromatogram into slices, or otherwise known as modulation periods of, well, in this case, 2 seconds. But generally speaking, we can say that there are modulation periods from, let's say, 1 second to 7, 8 seconds. Where I just recently reviewed a paper where they actually used 9-second modulation periods, which is crazy. So what happens? The modulator basically traps the effluent from the first column in these 2-second segments, and then it reintroduces them into a second column, which is a very short column. It's a very fast separation. You see that you have basically 2 seconds to perform a separation on the second column. So in the case of thermal modulator, it can range to 15, 20 centimeters up to 1.5 meters. And in case of flow modulation, because of the use of higher flow rates, 3 to 5 meters. So basically what we are doing then is create these 2-second long little chromatograms that correspond to the length of a modulation. these 2-second long little chromatograms are placed after another, and that generates the raw data of the 2-dimensional chromatograms. So this is basically how the raw data looks like when it comes out of your instrument. Now, one important challenge in GC/GC is how to visualize the data. Now, because this is very nice, but you know, there is a nicer way of representing the data. So there are some specific softwares that are graphical softwares that help you with the representation of GC/GC data by generating these 2-dimensional chromatograms, or otherwise referred to as contour plots or heat maps. So how is this made? So as I just mentioned, the raw data basically shows itself along the y-axis. So the y-axis here is the second dimension retention time. The x-axis is the first dimension retention time. So we take the slices from the raw data files because we know the modulation period. So we know exactly how long the slices should be. And then the software basically lines up these slices of the raw data chromatogram. Then it detects peaks with the same second dimension retention times. You see that here is this peak here that rises and falls as it elutes from the first dimension column, and it appears exactly at the same second dimension retention time. Now, the second dimension retention time is assigned to this peak. And then what happens is that the software, looking at the height of these peaks, fits a Gaussian curve to recreate the first dimension peak shape as it would appear. But it's important to note that this is in theory. So this is a regenerated first dimension chromatogram, basically. And then thereby the retention time 1 and retention time 2 are assigned with this mechanism. Now, it's very important to note here the rule of thumb that since the 2D GC works this way, we need to have at least 3 slices of each individual peak, because if we don't have it, then it's going to be very difficult for the software to fit a Gaussian curve on top of, let's say, 1 or 2 peaks. All right. And then the z-axis is the intensity or the signal strength of the peaks. And this is intensity axis is basically translated into some kind of color scale to generate a contour plot, which looks a little bit like this. This is a realistic representation of a contour plot. It's not idealistic by any means. Okay, now another cool thing that these softwares can do is to do multi-projections. So what does that mean? Like you can basically look at both the second and the first dimension chromatograms as a projection on the y and the x-axis. So as I said before, on the y-axis, you find the raw data. And the x-axis here is basically a regenerated or a reconstructed 1D chromatogram. So if you would run this sample on a 1D system, this is how it would kind of look like. You can see that the peaks are pretty square. So it kind of looks like a 1D chromatogram with a detector that is undersampling. So the data, and the data acquisition rate in brackets would correspond to the modulation period in this case. Okay, so this is basically how a nicely looking contour plot is presented. So you can see the first dimension retention time, second dimension retention time, and then here you see all these peaks that are separated in the 2D plane. This is another form of representation. This is sort of the surface plot, so to speak. I don't think anybody uses that for practical work, only for presentations, webinars such as this one. So it's nice to look at. Okay, so let's talk a little bit about data acquisition rate, because this is an important segment of dealing with the comprehensive two-dimensional gas chromatography. Now, here we see a usual one-dimensional chromatographic peak, which lasts something like 7 or 8 seconds on the baseline. Now, if we modulate this peak, and remember that modulation doesn't only connect two columns, but it also refocuses all the material that is eluting from the first column, the peaks get massively narrower. And this, of course, gives a lot of separation power and also boosts a little bit the sensitivity, because obviously if we assume that the peak area in total are going to be the same, and then the peaks are squeezed together this much, the peak height is going to significantly increase. Now, if we zoom in to that peak, we can see that on the baseline, it's somewhere around 200 milliseconds wide. And this is considered to be a fairly wide peak in comprehensive GC by GC, because this is performed with flow modulation. Like using thermal modulation, you get much narrower peaks, like between 30 to 80 milliseconds. Now, in chromatography, when we set up the data acquisition rate of our detectors, it is important to kind of keep in mind the rule that we would kind of want to sample the signal to get decent peak shape enough times. So as a rule of thumb, it should be somewhere between 10 to 20 sampling points per peak. Let's just go with 15 for the sake of simplicity. So if you want to have 15 data points of this peak that is 7 to 8 seconds long, you would want to choose the data acquisition rate to be 3 to 6 hertz, which is 3 or 6 times per second, basically. And in gas chromatography, any detector can do that. So if we're talking about the universal detectors like thermal conductivity, flame ionization, electron capture detectors, all can do that. And if we want to attach the gas chromatograph to a mass spectrometer, quadrupoles, Q-traps, triple quads, orbitraps, time of flight, all analyzer types will be able to follow that kind of data acquisition speed. Now, if we move over to GC by GC peaks, where we are dealing with peak widths of 1 to 200 milliseconds, and if we want to maintain the same kind of data acquisition rate, which is really important, especially later when we are going to do data analysis of GC by GC data with peak deconvolution, it's very important to have enough data points over a peak to efficiently to be efficient for peak finding. So in this case, we would have to use data acquisition rates of 75 to 150 hertz. Theoretically, generally speaking, 100 hertz would do. Among the universal detectors, flame ionization, electron capture detectors can do that, and some element-specific detectors like an SCD or an MPD. But as far as interfacing with mass spectrometers, only time of flights or some quadruple time of flight mass spectrometers can do that. So that's sort of the take-home message from that. If you want to interface GC by GC with mass spectrometers, the time of flight is your best bet. LICO offers the highest data acquisition rate, time of flights up to 500, as far as I remember. You can correct me later if I'm wrong. Agilent has a time of flight and a quadruple time of flight that can do 50, which is, well, not ideal, but it does the job. And I think Shimadzu has quadruples that have high scanning rates, but that goes up to 20 or I think maybe 40 hertz, which again is not ideal, but it does the job to a decent extent. So why is it good and useful to use GC by GC comprehensive multidimensional chromatography? Well, we can do qualitative and non-targeted analysis interfaced with a mass spectrometer, exploiting increased separation power and multiplying peak capacity. We can get very, very high peak purities, spectrally speaking. So peak mining and identification work becomes much, much easier, much nicer spectral similarities. So again, just to reciprocate what I just said earlier, time of flight mass spectrometer is probably the best way to go for qualitative analysis with high scan rates. So a little bit about how a non-targeted or qualitative analysis is generally being performed. To start with, we have our raw data. We have our two-dimensional chromatogram. We can do some kind of peak mining. It could be integration based if you have complete separation, or the convolution based, which is again very useful for peak finding in case there is some partial coelution, like in this peak. This is taken from 1D data, but it's very analogous. It works pretty much the same way. I would say LICO's software Chromatoph has by far the convolution algorithm as far as I'm concerned. But there are other softwares that tackle this in a different way, but maybe that's for another seminar to discuss if there is interest. So after this peak mining, we have our peak list. Then we can extract the spectra, do a library search on the spectral library of the National Institute of Standards and Technology, which has over, I don't know, 700,000 entries. We can use some retention indexing, do some peak filtering based on the library matches and the linear retention index proximities. Thereby, we can come up with a tentative identification list of the chemicals. And then after that, we can go from a top to bottom funneling approach towards suspect screening or targeted analysis later on. So if you have very nicely separated chemicals on the 2D chromatograms, this becomes very, very easy. I show you what this really means. If you, let's say, in 1D in a sample find a peak like this, and then you run the peak finding method and the library search on this peak, you get a terrible spectral match. So what are the options? Maybe I discovered a new chemical that is in the sample, or more likely, run it on GC by GC, do the modulation, and then you will discover that this peak is not exactly one peak, but it's kind of a mixture of some column bleed and two chemicals that coelute exactly and perfectly. So with GC by GC, you can actually separate these three chemicals. I know this is a bad example because there is no baseline separation from in this case. But anyway, if you check the spectra, you can see that there is some column bleed here. And this big peak here is a mixture of two different chemicals. All right. Now moving on, I would like to point out a really, really cool feature of comprehensive GC by GC, and that is chemical information, or let's say inferring some chemical information based on chromatographic and retention time data. So again, go back a little bit to the types of stationary phases that we can find in capillary chromatography. Let's say if we take 3 chemicals, these 3 chemicals have exactly the same boiling points, but they differ from each other in terms of their polarity. If we do an isothermal separation of these 3 chemicals on an apolar type column, then the chemical that is the least polar will be the most retained, and thereby it will have the highest retention time. So it will be latest on the chromatogram. If you take the same 3 chemicals, separate them under isothermal condition on a polar type column, the order will revert, and then the most apolar chemical will have the least, and the most polar chemical will have the highest retention time on a polar column. So we can kind of correlate these physicochemical properties of these chemicals to retention behavior on certain column types. So let's start out from something that is referred to as the standard column configuration in comprehensive 2-dimensional GC by GC. Now, in this situation, in the first dimension, you would have an apolar column, like a DB5 style column. And then in the second dimension, you would have a DB wax, which is a polyethylene glycol type polar column. Then you would perform your 2D separation on this. Let's just jump ahead after method development. The method works fine. This is a mixture of standards here that we can see. What kind of chemical information can we infer from this? Now, what we can do is basically correlate the first column to the boiling point of the chemicals. Why not the hydrophobicity? The hydrophobicity, like I said before, is because we are running a temperature program in the GC oven. That means that what we will see in terms of elution order on the first dimension will be much heavier, much more correlated with the boiling point rather than the chemical or the column chemistry, so to speak, because we are not running isothermal separation. So we can say that the x-axis will be correlated with the boiling point and with the hydrophobicity a little bit, but mostly with the boiling point. On the other hand, since the second dimension separation is instantaneous, it goes really fast. Like it's a 1 second modulation period in this specific case. So it takes 1 second from the chemical to go through the second dimension column. In this situation, nobody cares about the temperature and the boiling point of the chemicals. This property is mostly going to be, or the second dimension retention time is mostly going to be associated with column chemistry. So just to prove that I'm not just talking nonsense here, I actually took 6 chemicals from a sample some time ago. I looked up their boiling points and their log KOW values. A KOW is basically the measure of hydrophobicity. It's the octanol water partitioning constant of a chemical. So basically, the higher this number is, the more apolar the compound is, and the lower this number is, the more polar and water soluble the compound is. So if we look at the boiling point correlation with the first dimension retention time, decent, not crazy good, but tolerable. And then you can also see that the second dimension retention time is indirectly proportional to the log KOW values. This value is often referred to as log P value as well. So after I figured this out, a few months later, I decided to do the same thing, but with 250 compounds. And now you can see that actually the boiling point correlation of the first dimension retention time is pretty cool. It's almost 1. Pretty good R-square for a correlation. The log P versus retention time 2 is a bit more sketchy. It depends. especially since there were a lot of chemicals in this sample mixture that were totally different from each other, chemically speaking. This correlation works much better if we are looking at homologous series of chemicals. But anyway, I would say that 0.65 is not a bad correlation. So we can say that, you know, there is some sense in what I just said earlier. Another thing I would like to show right now is something referred to as the inverted column configuration. It's not consensus in the GCxGC community, but this is how it sort of ended up developing throughout the years. In this situation, we have our first dimension column to be something a little more polar or something more aromatic. So retention time 1 will be more correlated with boiling point again, but instead of factoring in the hydrophobicity, polarity is going to be the parameter. So it's going to be basically the other way around. So a little more polar chemicals will be more heavily retained. And then as the second column, we have an apolar type column, and this can be reflected here really nicely. So the most apolar compounds are the most retained. This column configuration is pretty widely used in petroleomics or any kinds of applications having something to do with hydrocarbon analysis. So the least polar compounds are going to be the most retained, in this case, the alkanes. If you check the log P values, they're pretty consistent. So alkanes would always have the highest log P values, and then polyaromatics will always have the lowest ones. Okay, how are we doing on time? 32 minutes, perfect. Okay, now I will not quickly, but I will go through the 2 basic types of modulators that are available on the market. I will start with the flow modulator. This is in not any kind of order of importance or emotional commitment or anything like that. It's just, you can call it alphabetical, maybe. Not on purpose, though. On this picture, you can see the capillary flow technology flow modulator of Agilent. There are different types and different incarnations of the flow modulator that sort of kind of use variations of the same technique, but with higher or lower efficiency. So the concept here is that we have our first column that is connected to this capillary flow device. We have a very, very low flow rate of 0.5 milliliters per minute. Why? There is a fixed loop here in the modulator. It lies between these 2 connectors. This is really, really narrow. It's a capillary with a volume of 19 microliters. In this specific case, it can be changed with other instrumentation, but in this case, it's 19 microliters. If you translate this 0.5 milliliters per minute into microliters per second, it's going to be 8.3 microliters per second. So the fixed volume of this loop puts your method into some constraints as far as the first column flow and the modulation periods that you can perform. So what do I mean by that? So you can only trap 19 microliters of effluent from the first column. If you are using a column flow of 0.5 milliliters per minute, you can basically fill this loop theoretically for 2.3 seconds or something like that. So that's the maximum time that you can choose for a modulation period. And if you don't adhere to that rule, or maybe not rule, but constraint, then what you will do is you will generate overpressure here and that will mess with the method. It will change the pressure points, and then the whole thing goes up in smoke. Well, not really, but you know, it will mess up the method basically. So, and then as the second stage, this loop is being emptied through a valve that is externally placed outside the GC oven. So there are two modes of the modulator. There is the divert mode, which is basically we're collecting the effluent coming from the first column into this loop while we are purging the second column with the flow of 20 milliliters per minute. Now, this is happening 98% of the time of the modulation period. And then for a very, very brief moment, we switch to inject mode. And due to the narrow diameter and the small size of this sample loop and the high flow velocity that is coming out, the samples are refocused very, very efficiently. So we get the refocusing effect that will boost our sensitivity and also will boost the efficiency of the separation. So when we are doing modulation with the flow modulator, this is what happens. Collecting, inject, collecting, inject, collecting. So it's basically happening really fast, the injection. So now I will talk a little bit about some potential issues with the flow modulator. And this is based on the fact that we are essentially performing both separations on column 1 and column 2 under suboptimal separation conditions and suboptimal column performance. So this is a good old-fashioned Van Deemter curve. And you see that, maybe I jump to the next one because it's kind of nicer to present. So the optimal linear flow velocity, where we would have the best or the highest efficiency separation, if we're taking a standard 0.25, 0.25 column, would be around 40 centimeters per second here. And as you can see on the first dimension column, we are around here at the 10 centimeters per second mark. And in this situation, the band broadening is being determined by this B, which is the longitudinal diffusion. And that is basically coming from the fact that the flow velocity is quite slow, and the chemicals in the sample band has a bit more time to broaden due to longitudinal diffusion in the capillary column. Now, on the second column, though, we are running at very, very high linear flow velocities. And in this case, the efficiency of the separation is being deterred a little bit by the very inefficient mass transfer between the stationary and the mobile phase described by this C factor. So to compensate for this in flow modulation GC by GC systems, we actually put 4 or 5 meters of second column after the modulator to kind of compensate for that inefficient mass transfer and to get decent enough separation. Okay, this is how a flow modulated GCGC system looks like in the real world. So here you have the 2 columns coiled up in the same GC oven. You will see that it's a bit different with the thermal modulation system. And here we have the flow modulator. First column comes in here, second column goes out here. And then here we have a passive splitter. Now, why on earth would we put that in there? Like, to complicate our lives a little bit more. The reason for that is that you know, since we are working at flow rates of 20 milliliters per minute, if you want to interface a flow modulated GCgC system with a mass spectrometer, mass spectrometers kind of accept up to 2 to 3 milliliters per minute as a flow. So if you want to pair up a flow modulated GCgC system with a mass spectrometer, you would have to split before. So in this situation, we are splitting away most of the flow after the second column, going into a universal detector or a sniffing port, or, you know, whatever you want to do with that. It's up to you, up to the creative minds. And then the rest of the flow, 2 to 3 milliliters per minute, goes into the mass spectrometer. So pros and cons. Pros. We do not need to use liquid nitrogen or any coolant for modulation. That's kind of nice. The modulation is not temperature dependent. So if you have very low boilers, excuse me, then this method is perfect for separating them, because the modulation will not depend on the temperature, because it's flow modulated, obviously. It works really well for non-MS detectors, so like FID-ECD, because these detectors have been developed during the times when the optimal, when packed columns were used. The optimal flow rates were between 20, 25, 30 milliliters per minute. So you can just go directly into these detectors without adding any makeup flows. And from a consumer-friendly point of view, it's relatively easy to work with the CFD splitter connections. Yeah. Cons. Uses a lot of carrier gas, which is becoming more and more of a problem these days as the price of the helium rises. Due to the fact that these sample loops have determined volumes in the modulator, the parameters are quite interlinked. So you cannot just go there, okay, I need more retention, so I'm just going to change this flow. No, and it doesn't really work like that. You really carefully have to think about which parameter you want to modify, and what other parameters will it have effect to. So it's actually, from a method developmental standpoint, it's a bit more tricky to work with. You need to split the flow before going into a mass spectrometer, and thereby deteriorating the sensitivity, or have a negative effect on it. And we are working with suboptimal flows, thereby having a bit worse chromatography. But on the other hand, with GC/GC, it's, you know, it's not always about having the super optimal flow conditions at each column, even though it's possible with the thermal modulator. So this is a conceptual figure stolen from the LICO instruments. Basically, you have two jets, and there is pulsed cooled nitrogen, liquid cooled nitrogen coming in through the cold jets, and hot air going through the hot jets. Basically, I know I'm out of time, so I'll speed up a little bit here. We have 4 stages of modulation. First, we have the first jet cooling, where it collects the effluent from the first column. Then we have the second stage, where the first jet gets hot and the second jet gets cold. And then we have the third stage, which is super important, where both jets are cold. If you didn't have these 2 stages, then you would have a problem, because if you would have the hot stage, you would also have the effluent still flowing. So your baseline on the chromatogram will not be the best. So this is a very ingenious design, and works really, really nicely using liquid nitrogen and hot air. This is how the modulator looks like. Now, you actually have a secondary column here in the secondary oven. which can be programmed at an offset to the primary column. And this is basically how the modulator looks like. These are the cold jets here, these tubular-like objects, and then you have the hot jets on the side. Now, you have to, well, no, you can program your primary oven and your secondary oven and the modulator with the temperature offset. These are the standard values that, in this case, LICO suggests, which work really nicely. But if you want to manipulate second dimension retention, you can, of course, change the temperature of the secondary oven and the modulator. So this is basically how the thermal modulator refocuses chemicals eluting from the first column. So you see it's extremely efficient, especially for if we're using liquid nitrogen. So pros and cons. Very sharp peaks, 30 to 50 milliseconds, at least twice as good as the flow modulator. We can work with optimal flow rates. We don't need to split after modulation. Thereby, we can get better limits of detection, limits of quantification. Cons, if you want the good stuff, which is the liquid nitrogen modulator, it uses a lot of liquid nitrogen. You can also substitute that with an ethanol coolant, but in that case, you have to say goodbye to modulating to your low boilers. I would say lower than 80, 100 degrees in boiling point. And maybe it's a little more annoying to work with, practically speaking, because, you know, in the points of the modulation, you're heating and cooling the column from -100 to 350 every 2 seconds or every 3 seconds. It really puts a tear on the capillary. So the moment you touch it, it snaps. So you need a bit of patience and some calm nerves and well-developed nervous system to work with that. Altogether, I did a shootout of thermal and flow modulation. Cost effectiveness, flow modulation wins by a little. I actually added this one because of the higher helium prices in the last few years. Peak width, thermal modulation is definitely superior, but flow modulation can also get peaks of 50 to 100 milliseconds wide if the method is developed correctly. Using thermal modulation will gain you a bit more sensitivity and detectability. User friendliness, despite the fact that maybe thermal modulation can be a bit annoying to work with, practically speaking, you can actually go in and modify one parameter without, destroying the house of cards, like as you would do with the flow modulation. And as far as compatibility with the mass spectrometer, I think thermal modulation is also winning this one because, again, it doesn't use very high flow rates. So altogether, thermal modulation wins 6.5 to 4. And I think it's time for me to stop here. I overshot a little bit. I'm sorry about it. So if you have questions, then I'm happy to take them.
So thank you for the presentation. It was quite thorough, if you ask me. You mentioned something about the scan rate of the LECO mass spectrometers at some point, and yes, they can do 500 hertz.
Yeah.
Both the old Pegasus 4 and the new Pegasus BT.
Yeah, I wasn't sure about the BT, how fast you can go with that. So
internally, it works with 35,000 transients per second.
But, oh yeah, that's crazy. It's crazy.
Sums it up to like 500 or less scans per second.
Okay.
So we actually have a question from Thijs who asks if it wouldn't be ideal to use a pressure controlled split point.
Are we talking about flow modulation?
Yes, I think so. The question came in when you were talking about flow modulation.
You could easily use that. Actually, you can introduce even a Dean switch. there. In this system, this picture was taken of actually the system here in the lab. Wait, yeah, it's there. And we're using a passive one. So basically, we just use capillaries with different dimensions and calculating with the pressure difference at the endpoint. So since one goes to the mass spec, you calculate with P0 in the Hagen-Poiseuille equation. So you kind of use that to calculate the split ratio. But sure, you can use a controlled pressure point with the makeup flow as well, if you want to manipulate that a bit more, if you want more control. Thank you for the participation. I appreciate it. A lot of people came, so I'm glad about that.
Yeah. Thank you for taking your time to talk.
Of course.
I wish everyone a nice afternoon and a nice evening. So,
Me too.
Yeah. Goodbye.